Hi, and welcome to the second lecture of our control course. Today we introduce the basics of control theory. So we go in the same way as we went last time, where we introduced the basics of systems theory. So for this, we start with something very similar to last time, when we said everything is a system. So from very simple things, such as maybe a bicycle or a heater, to more complicated things, such as a robot or a power plant, everything is a system. And we said that a system is in general defined as a device or a phenomenon which can be synthesized as an interconnection of parts. But in this lecture, this definition is now not enough anymore. So we have the system, yes, but we want to control it. We want to obtain something out of it. We want it to behave in a certain way. So we want to control the power plant in order to do something, or we want the heater to heat a room to a certain temperature, or the bicycle to do something, or the robot to do something, whatever it is. But we want to be able to control it. But then the thing is, what actually means to control a system. So we have a system which is similar to what we saw last time, right? We have a block with input and output, so the independent and dependent variables, the cause and effects that we defined, and we have a disturbance that acts on a system and might alter the normal behavior, the standard behavior of the system. And in this case here, we have something else, which is a reference. So we want a desired behavior to be imposed to a system. So to control a system means basically that given a reference, so given a desired reference, a desired behavior, we want to choose the right input such as the error is 0. And all of this needs to happen despite the disturbance. So this is what we defined last time to be the synthesis in the control engineering. So to synthesize a controller, to synthesize another system, basically, which is the controller that actually makes our system behave in the way that we want it to behave. And I just said that the controller is basically another system, because it actually is. So we have the process, and the process, or the system that we're trying to control, takes an input and gives an output. And what we want from the controller is basically to take an input, which is the desired reference that we want, and give an output, which is the perfect input for the process to be controlled in a certain way. So basically, the controller is itself a system. In this way, we have them both in the Laplace domain. If you remember, this Laplace domain is indicated by the S, which is this complex variable, which we use to go from the time domain to the frequency domain. And yeah, the controller is actually a system. Now, there is a problem in this block scheme here, because we said that we want the process to behave in a certain way, so to follow a desired reference. And this happens thanks to the input that we're giving, and the input is computed by the controller. But in this case, the controller is actually not aware of what's going on here. So the controller is not aware whether this Y, this output that the process gives, is actually the same as the reference that we're giving or not. We have no idea. So the problem is that the output here does not affect the control action. So the control action does not know what the output of the process looks like, and therefore is somehow limited. It's like it tries to control the process in a blind way, because it does not know what happens after a process. So there's no feedback. There's no feedback from the output, to the controller itself. So there's no way to ensure that desired behavior is reached. This you can imagine quite simply, like with the manual heater that we also have seen in the slides, in one of the first slides. So imagine you're in a room and you're cold. You turn on the manual heater. The manual heater is a system. It's the output that it gives is actually heats up the heater itself, and the room naturally gets warmer. But then you don't know whether the room gets warm up to a certain point, to a desired temperature that you would like to, because the heater just gets warm. So there is no way to control actually the temperature, because there's no feedback. I will now give you a more practical example also more visual and not just by talking about it, which is traffic lights. So we have a crossroad here, and there are some traffic lights, so there are some cars going around and some cars waiting for the traffic light to become green. And now the open loop controller, so this thing with no feedback from the system itself, you can imagine as something like the traffic lights they don't care about how many cars are there, but they just switch every 30 seconds. And so there's something like this where there are more and more cars coming from these directions, so cars accumulate and there's traffic now, while in these directions where the lights are green, at the moment there's no one. So there's no adaptive traffic light switching, but there's just time-based traffic light switching. And then the open loop controller basically creates traffic because there's no one here passing through while there's a lot of people now accumulating on the other side. So this is somehow the limitation of the open loop controller and why it's not ideal to have no feedback from the process when possible, of course. So how do we solve it? How do we solve this problem? Well, I mentioned the word feedback many times, and I did because it's actually one of the core words for control systems. So we do need feedback from the system, and to do that, we have to measure what comes out of the system, and we want the controller to somehow adapt its action, adapts the output that it produces, which is the input for the system, to whatever it reads from the system itself. So the controller would have the reference and will have what the system is providing, compare them and say, oh, I need the action to be more on this side or on this other side, and trying to adapt whatever is going on. So the closed loop controller, the block scheme for the closed loop controller, so the feedback scheme, is something like this. We have a controller that provides a certain input to the system system provides a certain output. This output is measured and it's compared to the reference. So basically, reference minus the produced output from the system is the error, is this error in reaching the desired state, in following this desired reference that we're giving, and this is fed to the controller so that the controller can adapt its action. And again, from a very visual point of view, open loop versus closed loop is something like this. In here, we have open loop. We have the manual heater because you're cold, you turn on the heater, and the room eventually gets warmer. You don't know how warm, you don't know if you want 22 degrees, you have no way to ensure that because there's nothing that is actually measuring the state of the system. While in this case, you have a sensor, the sensor is measuring the state of the system, is measuring that the room is at 19 degrees, and so it actually keeps the heater on. And when the room hits the desired temperature, whatever it is, actually this switches off the heaters and tries to keep it balanced, to keep it equal to the desired temperature. So open loop against closed loop. One measures the output of the system, one doesn't. So we need to measure, so we need sensors. So in here, there will be something that has to measure. So there are some sensors that need to measure the output of the system. And the controller, as I said, is self-regulating thanks to the error. So it changes its action in a dynamic way based on what it reads from the sensors and what kind of error it's dealing with. Of course, the goals that we have with such a system, with such a closed loop system, is that the system has to be stable. Of course, this is our main concern. It's something we introduced last time, all the stability theory, and it's important for us because we need the system to be reliable, to be stable and to work as we expect, with no surprises. But also, we would like that the output behavior has to be the same as the desired one. So we don't want to give a reference and then we have a constant error. We are not able to reach a reference for any reason because that will be quite useless. You are setting 22 degrees in the room and your controller just eats up to 20 or to 24, and that's obviously not what you'd want, not ideal. So we have to be able to get an output behavior which is exactly the same as the desired one. So these are the goals. What are the bad things about this kind of scheme? What are the limitations? Well, the limitation is that we need to be able to measure whatever we are interested in. So whatever it is that we are trying to control, it needs to be a measurable thing, it needs to be available, and the sensors must be good. If the sensors are not good, they are giving a wrong measure to the controller, which will result in a wrong error, which would result in a controller giving a control action which is not aligned with what you want. It doesn't actually deal with what's going on, which is a problem. It's a big problem because then the controller is basically controlling, trying to hit a set point which is something else, which is something that you are not specifying, and that it might be dangerous in some cases. So main limitations are related to measure in general. So being able to measure and being able to measure in a very good way, in a very reliable way with a high accuracy. Now, let's go a bit forward with the closed loop. So this closed loop scheme, as I said, there are two systems in here. When we have systems, interconnected systems like this, basically what happens is that we have two transfer functions, and the resulting transfer function is just a product of the transfer functions we have. So here we want now to have a look at the stability theory and all of the important quantities that we have for systems. And so we're trying to introduce the transfer function. We do everything for now in the Laplace domain. We'll come to the time domain later for some other specification. So as said, we have two transfer functions here, and basically they can be synthesized as a single transfer function, which is the product of the two transfer functions. So we have G, which is the controller, and we have P, which is the process that we're trying to control, and the product of those becomes F. F is our transfer function. So last time when we introduced the transfer function, I introduced this input-output transfer function, and I told you this actually gives us the whole behavior of the systems from the input to the output. So we introduce also concepts such as controllability and observability and so on and so forth. So we would like to have one quantity that basically connects the input to the output. So we know that everything that happens when we feed something to the system can be described by this transfer function. This is what we did last time, and this is what we want to do also now. So here also we want something that completely describes the output based on the input. And the input in this case is R, is the reference. So given a certain reference, we want something that describes the behavior of the systems up to the output. Well, you can see from here that the output is actually equal to F times the error, where the error is equal to the reference minus the output itself. So it's something like this. So then we can just solve it for Y, and we get this thing here, F over 1 plus F. Remember that F is a transfer function, so it's actually a fraction. So here we will have to, you have a 4 layers fraction, you just have to rearrange things. But this is the new input-output transfer function. So this is what we care about. This is what we want. And as I said, this is a fraction. So if it's a fraction, we can write it like this. It's a numerator over a denominator, and then you just rearrange things. You can do the computation. You should end up with something like this. So we have basically a transfer function which describes the input to output behavior. And basically what happens is that the denominator of the transfer function, of this resulting transfer function here, which is where the poles are, where the eigenvalues are. So if you remember the last lecture where we said that the poles of the transfer functions, which are the root of the denominator, are actually eigenvalues. And this denominator here is the numerator plus the denominator itself, because it's not just f, but it's f over 1 plus f. So you won't have just the denominator of f here, because there's some computation to be done. So do not confuse f by itself with the closed loop transfer function. F is the open loop transfer function, because if there was no feedback, you would just have an input, F, and the output, and it would be the open loop transfer function. But we are now interested in the closed loop transfer function. So this is the new shape of the transfer function, and we want the system to be asymptotically stable. So we want all eigenvalues to have a negative real part, as we introduced also in the last lectures. And we know that the eigenvalues are roots of the transfer function. Now, we also said not necessarily all eigenvalues are in the transfer function, but we know whatever we find in there is actually an eigenvalue. So for now, let's forget about this case in which there are some eigenvalues that are not actually part of the transfer function. We will come to that later, but for now, we have everything in there. So we have a controller. We put a controller. The controller, we said, is a dynamical system that we are designing in some way to control the system that we're dealing with. And we wanted to design such as this denominator, so the denominator of our transfer function has only negative poles, only negative roots. How do we do that? How much freedom do we have? Well, we have a necessary condition for assigning the eigenvalues, which is this condition here, which seems unreadable at the moment, but actually it says that the degree of the polynomial of the transfer function that we're dealing with, which is nf plus df. So nf plus df is the denominator of the transfer function, and we're looking at its degree because it's a polynomial in S, where S is the variable, is the Laplace variable that we're dealing with. So the degrees of the polynomial must be able to the degrees of freedom of the controller. So when we design the controller, it's a dynamical system. We will have some degrees of freedom, and we need these two numbers to be exactly the same. Now, I understand that this might sound a bit abstract, and that's why there is a small example that will hopefully clear your mind. So we have a process, we have a system which has a certain transfer function and has two eigenvalues. Now you can easily see that the eigenvalues are -1 and +2, so the system is unstable. We have an eigenvalue on the right half plane, a positive eigenvalue, an eigenvalue with positive real part. We want to design a controller. So usually when you do something like this, this is a synthesis done by attempts, so-called attempts, because you're just trying to design the minimal dimension controller that is able to stabilize the system. So the first controller, the simplest controller, doesn't even have an S, because it's not really a transfer function, it's just a gain. It's just A, so there's no fraction in there, there's no complicated system, it's just something based, it's something similar to also what we've seen in the bicycle. It's just the simplest thing as possible. And we can easily see that there's only one degree of freedom for the controller, which is A. A is a number, and we can choose it. This is the only degree of freedom we have. What is the denominator of the transfer function? So it's nf plus df. Now, nf, when we do the product between this and this, nf, the numerator of f, will just be A. And here we have it. While df will just be the denominator of p, because this has no denominator. So it will be s plus 1, s minus 2. So the polynomial has degree 2. So we have a polynomial of degree 2 and 1 degree of freedom. So the equality that we have mentioned before is not satisfied. So this does not work out. So we have to increase. We have to go one dimension further. So we do something like this. A transfer function as a controller that has one pole in minus b, we can choose b whatever we want. So if we choose b to be a positive number, the pole in minus b will be a pole in a negative, with negative real part, which is fine. And it has no zeros, so there's just again the gain a. So again, we do the same computation, and we end up that the degrees of freedom of the controller is 2, because we have now a and b, which is nice, because we got to the same number of degrees of freedom we had before in the transfer function. But this time when we do numerator plus denominator, the numerator is still just a, which we have here, but the denominator is the product between this and this. So we have a degree, we have a polynomial with of third degree. So with the highest power is 3. And again, this equality is not satisfied. So this is not what we want. So we introduced a 0 also in the controller, and this would solve the problem. So if you do the computation, you end up with it. Here we have A, B, and C, so 3 degrees of freedom, and in here you have a polynomial of degree 3. So the equality is satisfied. This thing is actually able to control the system and to make it stable, because you can choose A, B, and C however you want, in whatever way you want, to have all poles, so all poles of the closed loop transfer function to be negative. This is nice and easy. So we can always design the controller in the way we want. The thing is, can we always assign all the eigenvalues? So are we able to force all eigenvalues all the time? Well, of course not, otherwise it would be too easy. We have to take again one concept that we introduced last time, is the controllability and observability. So if you remember, we have controllability and observability as two conditions for an eigenvalue to appear in the transfer function, as a pole of the transfer function. And so an eigenvalue lambda I, in order to appear, has to be controllable. So the rank of this matrix should be equal to n, so it has to be full rank, where n is the dimension of the state variable, and the rank of this other matrix here should be also equal to n, and so the eigenvalue must be observable. Where I remind you that these lines here are basically indicate the juxtaposition between matrices. So you have here the matrix A minus lambda I, and then on the side you put B, and then here you have A minus lambda I, and at the bottom you put C. So these two conditions must be satisfied in order for an eigenvalue to be controllable and observable, and all the others cannot be changed. All eigenvalues which are not controllable and observable are hidden eigenvalues, and they cannot be changed. So intuitively, this is also an intuition we gave in the last lecture. Controllability means that the controller can act directly on them, and observability means that you would see the evolution in the output. Also, you can imagine that when you have this input-output transfer function, so this closed loop input-output transfer function that we built, it means that something can be reached by the controller, so the controller can act on it. The other one has to be seen as the output. So this is the somehow the intuition behind it. Now, based on this, we can actually, like, it would be nice to have a shape for the system to say, okay, from this shape, I can see what eigenvalues are both controllable and observable, what eigenvalues are not, and maybe they're only controllable, or maybe they're only observable, or maybe they are neither. Actually, these exist. So all of the systems, when we are in the time domain, is described by matrices. And since the system is described by matrices, you can find other matrices, which are invertible, which happen to be a change of coordinates. So you write your system under new coordinates. This is in general always possible, and every system can be rewritten under a change of coordinate in this way. This is a very peculiar structure, as you can see, where the matrix A is block triangular. So below the main diagonal, there's all zeros, and also matrix B and matrix C have a very peculiar shape. So when we write this and we just expand the vectors, we end up with something like this. And this is called Kalman canonical form, and it's canonical because what happens is that you have a clear separation between controllable and observable eigenvalue. So here you have that the eigenvalue that belong to x1 and x2 are controllable because the input appears in the equation of x1 and x2. In fact, if you remember B, the matrix B, which is the matrix, the control matrix, the one that relates the state and the input, matrix B was something like B1, B2, 0, 0. Means that these two eigenvalues are controllable, or the eigenvalues related to these two state variables are controllable, and the eigenvalue related to these two variables, to these two state variables, are not controllable. Similar intuition for the observability. So we have that the eigenvalue that belong to x2 and x4 are observable because they appear in the output equation. And all the others, so x1 and the one related to x1 and x3, are not observable. And also for this, you remember that the shape of the C matrix was 0, C2, 0, C4. So only where you have non-zero entries, you have observability. And so in this way, basically you have everything that is observable, controllable, and observable. Like for example, x2 appears both in here, so it has the input, and appears in the output. So x2 is controllable and observable. x1 is only controllable because it does not appear in the output equation, but it has the input applied on it. While x4, on the other hand, is only observable because it doesn't have the input, but it appears in the output equation. While x3, which is the only one left, it has no input and it's not in the output, so it's uncontrollable and unobservable. So you have a clear separation between all blocks, all properties, so to say. But now, like, we have this change of coordinates. We have x1, x2, x3, and x4, which, as I said also in the very first lecture, we are dropping the bold notation because it would make it very heavy. But this could potentially all be bold because x1 doesn't need to be one state. It could be a stack of states that share the same properties. So what is the number of these eigenvalues? What's the number of eigenvalues that are controllable and observable, or that are just controllable, or whatever? Well, there are some tests, and here you can build a matrix which is B, A, B, A square B, and so on and so forth until A n minus 1B, and the rank of this matrix gives us the number of controllable eigenvalues. Again, this you know, how to check whether one eigenvalue is controllable. So basically you can know the number of eigenvalues. You don't know which ones, but you know how many. And then once you find the eigenvalues, you can check, oh, is this controllable, yes or no? Is this controllable, yes or no, and so on and so forth. Where n is again the state dimension. Similarly speaking, it's for observability. Observability is something like this. It usually goes in the vertical direction rather than in the horizontal direction. So we build the same matrix. Remember before it was B, A, B, A square B, and so on and so forth. Here we have C on the other side, so it's C, CA instead of AB as it was before. So it's on the left until CAN minus 1. And so with this rank, you can you can find out how many eigenvalues are actually observable, and then you can check for the observability of a specific eigenvalue. Good. Now, we do a small example. We assume to have a process that has no hidden eigenvalue, and it has a controller. So we have a process here, s plus 1, s minus 2. S minus 2 is the denominator of the transfer function of the process. It has one eigenvalue in plus 2. So this system is unstable. We have a controller, which is already given. It's 1 over s plus 1. And the open loop transfer function, so the transfer function that results from this is something like this. Because the s plus 1, once we do the product between these two, s plus 1 will just simplify with s plus 1, and we end up with this. Well, it doesn't mean that this system, the resulting system, has only one eigenvalue. the number of eigenvalue of an interconnection of system, you can stack how many systems you want together, but the number of eigenvalues is equal to the number of eigenvalues of the individual systems. So basically what happens here is that P has one eigenvalue, G has one eigenvalue, so the resulting system has two. The actual transfer function we have is something like this, is because it has the s plus 1 coming from G and it has the s minus 2 coming from P, and it simply has one hidden eigenvalue. So there's one eigenvalue that, because of some simplifications, because of interconnections, it simplifies, it becomes hidden. So it becomes either uncontrollable or unobservable, but it's just hidden. And this is the main problem. So interconnection between systems, even when you put a controller there, can actually create hidden eigenvalues. So it's not something that it stays within the limits of your system, of the process you're trying to control. It might have hidden eigenvalues or not. But also when you put the controller there, you can create more hidden eigenvalues, which might be a problem. Of course, if all the eigenvalues that are hidden have negative real part, so they are negative, then the process is stabilizable, because you don't have any hidden eigenvalue, which is somehow something we cannot influence, which cause an unstable evolution. So the process is stabilizable. So I just want to give you now one intuition about these hidden eigenvalues. So we have an interconnection here, and we have a simplification, s plus 1, s plus 1. This simplification is called pole to zero, because the system evolves in this direction, and then we have the pole first and the zero then. So this is a pole to zero simplification. A pole to zero simplification causes an eigenvalue, causes a hidden eigenvalue to be unobservable. Why? Well, intuitively, it's something that it's a simplification, it's an eigenvalue that comes from the controller. So the eigenvalue belongs to the controller. Since it belongs to the controller, it's something that you can actually design, so it's not uncontrollable, because it is the controller itself. It's just something that happens to be a simplification, but it's something you can tune in the controller. So it's not uncontrollable, but it's unobservable. On the other hand, if we would have a zero here, which would simplify 0 to pole, in that case it would be something uncontrollable, because it's not something that the controller can deal with by changing its poles, because it's an eigenvalue that belongs to the system itself. So this is just an intuition to more or less understand how do uncontrollable and unobservable poles appear. It's not strictly part of the course, but it was just to also give you some sort of understanding of how are they created. Now, this somehow covers a bit the stability part and how to design a certain controller. Now, I want to talk to you about the response of a control system a bit, because you know that when you, for example, set something in the heater, like in the electronic heater that has the sensor and everything, so there's this closed loop system that eventually brings the room to the temperature that you want. It's not like the room reaches that temperature in no time and it stays there super stable, there's absolutely no error and so on. Like there's actually some evolution, there's actually like a build up to the desired state. So imagine, this is a slightly different example, but the concept is the same. You are opening a tap and you want water to a certain temperature, so you're putting it warm, for example, and what happens is usually something like this. The water starts at some initial point, which is not necessarily the one that you want, so this would be the desired state of water. The water is a bit colder than that, so it actually gets warmer, but it gets a bit too warm usually, and then somehow it converges back to the the desired state. This is, I think that you can all relate to this situation when you shower, for example, when you wash your hand or whatever. Like, this is somehow what happens. Well, in here we can already find two main areas, two main situations. One is the transient. The transient is when there's a big evolution, there's something that is somehow very far away from our reference, but there's just a system that starts evolving and tries to converge somewhere. And then there's the steady state. The steady state happens when we are fairly close to the reference that we've given, and we're getting there. Maybe we're not exactly there yet. We're very close, but the steady state is something that it's long and it goes on basically until the end of the evolution. So let's zoom in a bit on this graph. So we have time here, and we have the temperature of the water for your shower or from your tap or whatever. And there's a bit of nomenclature to introduce here. So one is the initial state, which it's quite easy to understand. It's just like, what's the initial temperature from the water? You open the tap, where does it start? Then we have a certain evolution, and then we have reaching the desired state. In particular, in this evolution, there's one important concept which is called overshoot. Overshoot is basically the maximum, the maximum amount of any quantity that you're measuring, in this case the temperature, that the system reaches after decaying and going towards the steady state. And then there is another thing, which is the steady state error. Steady state error is what I mentioned at the beginning of the lecture, that we want the closed loop system to be not only stable, but also to reach the desired reference. If it doesn't reach exactly the reference that we're giving to it, we have a steady state error. So steady state is basically, as I said, everything after the transient expires. So what happens to the system on the very long run. And we might have an error. Ideally we have none, but we might have an error. So again, a bit more formal definition about transient and steady state. The transient response was the very first reaction of the system to a change in its equilibrium. So, or to a change in a steady state, which is kind of the same concept. You have a system which is either evolving or it's just at rest or whatever. There's something coming to it, either an input or a disturbance or whatever it can be, and a transient happens. So the system starts evolving in a different way. It has to deal with whatever is coming in, so whatever is being fed to it. And then there's a steady state. The steady state response is the equilibrium is reached by the system after the transient decayed. So the total response of the system is a sum of these two, and the transient goes to zero as time increases. So at some point, while time passes, the transient is basically is something that is completely decayed and has no impact on the output anymore. So, as a recap of what we've seen so far, these were the two goals that we wanted to get, and honestly speaking, we talked about stability, we talked about this transfer function and how we build them and how we can design eigenvalues and so on and so forth, but we didn't say anything about this output behavior to be the same as the desired one. We didn't say anything about the steady state error to be zero, basically. Well, this is a bit of a more complicated concept, which will come in the next lecture. So for now, the important takeaway message is, what is stability? How do we deal with it? And how do we design a closed loop system which has certain eigenvalues and which one are hidden, or how to check for controllability and observability and so on and so forth. As last time, we closed with an example. Last time we talked about the bicycle, which I hope that you liked, and then we continue with this example. so that I can now introduce some controllers for the bicycle. So it would be a bit now more practical and not just describing a bike and saying, oh, this bike actually falls down or not, but to give you an intuition of how does the bike actually work and what happens when you do a certain action on the bike. Again, there will be some complicated models that we're not going to explain here. The physics behind these models is not going to be explained here. But as I said also last time, I will give you both the paper that introduced these concepts and a report that I did with some colleagues where there's all the physics derivation and there's some more intuition so that you can actually have a full understanding of the paper if you're interested in it. So, bicycle. We have the bicycle with a certain constant velocity v, which is positive. At the moment it's positive velocity. And so since we want to simulate the behavior of the bicycle a bit, we also gave it some values. So there are some normal values, so bike is actually pretty heavy. And we have stuff that happens and we are going at 4 meters per second. So it's just any bike. You can change these numbers and try to simulate, so try to build in your preferred programming language the model of the bicycle, since you have the transfer function, and see how changing these parameters changes the evolution. We will also talk about this front fork and the neutral model like last time. So if you remember, the neutral model was when this axis here is perfectly vertical, so there's the angle lambda is equal to 90 degrees and c reduces to 0, while then the front fork model introduces this angle. And when we talk about the front fork model, the angle will be 70 degrees. We will also deal with the neutral model, and in the neutral model case, of course, the angle will be 90 degrees, but as by construction, this has to be vertical. So we won't specify it then. We just say neutral model, you know it's going to be 90 degrees. This is again the 3D view of the bicycle with the relevant angles. I repeat the angles for clarity. So we have the tilting angle phi, which is basically how much the bicycle is tilting with respect to the vertical axis. Then we have delta F. Delta F is the steering angle. So the front wheel, how much is steering, which is usually an input or is the direct consequence of the input torque that you're giving to the handlebar. And then we have phi F, which is phi front, which is basically the tilting of the front wheel, because if the bike is tilted, but the front fork is also steering, then the front fork will have a tilting angle which is different with respect to the rest of the bike. So these are the angles, the important angles. Let's start with the neutral model. So angle that we mentioned already. This is the model coming from the physics, which we introduced last time, and it's exactly the same thing. So we have A, B, H, R construction. So you can find them all here. It's based on the length of the bicycle, the height of the bicycle. Then we have G, which is the gravity acceleration to the ground. So it's basically the gravity force to which the center of mass of the bicycle is subject to. And we have V, which is this forward velocity, because the bike is going forward. So it has a constant velocity that we said was 4 meters per second. Now, neutral model becomes something like this. So we have the state space representation of it, and we have the transfer function. We said that this transfer function is problematic because it's unstable. And we also gave the idea of why it's weird for a bike to be unstable per se, because we would expect it to be stable, because we would expect that the bicycle, if you go fast enough, you don't need to move the handlebar to be stable. You can just go fast without your hands. But again, it's not the real model of the bicycle, but still, we want to see whether it's actually possible to control it. Well, we introduced the simplest controller we can think of. So delta, which is the input to the system, has to be able to minus k times phi. So basically, what we do is that we want to have a steering. So k is positive. Assume k positive. So we want to have a steering which goes in the opposite direction to leaning, which makes sense. So intuitively, if your bike is leaning on one side, you want to steer it on the other side so you don't fall down in here. If you try to steer in the direction of leaning, this is not going to end well. So we just have the simplest controller where we steer in the opposite direction as leaning. Well, with this, you can substitute delta in the state space representation with minus k phi, and what you end up with is this transfer function. So this transfer function is actually like it might be stable. So you have to check this. You can check the eigenvalues, but I can assure you that this transfer function can be made stable if k satisfies some conditions. And here I show you two simulations. So I chose two gains for k. So there are two different numbers that I set there for k for having this evolution. And you see that basically both phi and phi dot, so the leaning velocity, converge eventually to 0. Of course, the evolution and also delta eventually goes to 0. So in the end, basically it says at some point I managed to be stable and I don't need to steer anymore. You can just go straight. So we reach an equilibrium. You can see that depending on the choice of k, the evolution is a bit different. So we have a more aggressive k, 0.75, with respect to the milder 0.63. And with the more aggressive gain in red here, you can see that the bike reaches 0 right away, but then there's a bit of oscillation. So there's a bit of overshoot, what we define as an overshoot. So it goes up and then has to go down again, because it's like you're leaning, maybe you are scared or something, and you steer quite abruptly. The bike goes in the other direction, but actually it leans a bit to the opposite side before going stable. So there's a behavior that is somehow, you can imagine like a pendulum, but inverted, so facing up. So it starts from here and it does something like this. While with k equal to 0.63, you can see that the evolution is maybe a bit slower. So you reach a stable position, like an upright position a bit later on, but there's no oscillation. So it's just a bit more gentle. The evolution is a bit more gentle. And it's also more gentle for phi dot. So this leaning velocity is actually very, very low in the case of the milder gain, while for this more aggressive maneuver, we have some oscillation. So the velocity is a bit more, it's a bit more aggressive in general. Now, I'll show you some simulation on the front fork model. So now we introduce this angle and all the things that we've said last time. And if you remember, we had something was like transfer function was actually quite complicated. And in this case, we use a delta, so steering angle that depends on two things. So one is the torque that you apply on the handlebar, because the delta actually depends on the torque itself. And one depends also on leaning. So you can imagine that these two things, one is caused by human. So the torque is caused by the human actually grabbing the handlebar and steering. This one is caused by just the normal evolution of the bicycle. So if you lean a bit on the bike, you can see that the front wheels tends to steer a bit to keep balance. So you can imagine that it's a behavior similar to this. So this is the controller that we are looking at. And now, how does the torque look like? What is the torque that we apply to the handlebar? Well, intuitively, we again try to steer in the opposite direction as leaning, because that's what our brain does. So if we're going on a certain side, we are naturally brought to steer in the opposite direction. That's true. But it's also true that there is, even if it's a very short time, we have to think about this. So we can design a control load, something like this. And I know that there's this one term which looks a bit weird at the moment. It's something we haven't talked about, but I wanted to introduce it in an example because in this way it's a bit easier to grasp. So the torque depends on the lean angle. So if the bike is leaning more, then we probably apply a heavier torque so that we try to go right back up. But there's also delay. This is a delay term, so it's in the Laplace domain, as you can see, because S is still Laplace, and theta here is a neuromuscular delay. So it's a delay that humans have when thinking of, okay, I'm falling down or I'm leaning a lot, I have to steer, and then you steer. So this process, which is maybe automated in your brain, still takes a tiny bit of time and it's not immediate. So we introduced it in this example in order to also show you how does a system with delay react and evolve. So first of all, what does a delay cause in a controller? Like we have this K, which is our controller. Like, are we able to stabilize this system despite the delay? Like, despite this term that we've never seen before, how does it work? Well, I will not go into too much detail in this thing. I will just give you one definition. So this is a controller, and you can imagine this thing, this delay is just not necessarily here in the controller, but it's just in the process, because we said that interconnection of systems is basically a single system. Well, we have a definition which is called delay margin. Delay margin is the maximum amount of delay that the system is able to withstand before becoming unstable. So there will be at some point a certain theta for which the system is unstable. And this you can actually imagine. So imagine that you are on a bike, the bike is leaning, you have to think fast. Okay, I'm leaning a lot, I need to steer. If the system, if the neuromuscular delay that we're considering in this case is like 5 seconds, then you fall down because you're too slow in taking the decision of steering in the opposite direction of leaning. While if the decision process takes 0.1 second, so you say, oh, I'm leaning, I just adjust it a bit. Oh, I'm leaning again, I adjust it a bit. Then you will be able to actually keep stability. So the delay margin is what is the max amount of delay that the system is able to withstand before becoming unstable. So technically what you can do is that you take your measures of your bike, of all the dimensions, of the mass of the bike and everything, and you know that if you're traveling at 5 meters per second and you lean for, I don't know, 30 degrees, you are actually able to calculate mathematically how slow can you be in steering in the opposite direction before falling down. So this is the idea behind it. So what is the simulation? What does the simulation look like? We used a certain K equal to 5. So here you can see that the system starts from a certain phi, which is half a radian, basically. And you can see the torque and the delta, so the steering. And you can see this step here. This step here is the delay. So we used in this a delay of 0.1 seconds. So the rider is skilled and is pretty fast in thinking, oh, I have to steer. And you can see that there are some oscillations, of course. The evolution is not as smooth as what I've shown you before. But overall, in the end, the torque goes to 0, phi goes to 0 as well, so the system becomes stable, delta goes to 0. So in the end, there is a bit of delay, there are some oscillations given from this delay because the system has to adjust and everything, but in the end the bike stays upright and straight. So this is what we expect. This is basically normal behavior on a bicycle. I want now to introduce a different model to give you an understanding of what's going on. And it's the rear wheel steering bicycle. So imagine that you are on a bike, but the wheel that steers is actually the rear wheel, not the front wheel. So basically what we can do is that we take the exact same bicycle and we say the velocity is now negative. So instead of going in this direction, we're going in that direction. So the way you phase is not important because we're not really thinking about a rider here. But then you're going in that direction, this is the steering wheel. So it's just a normal bike, but traveling backwards. This model, and you will find this on the paper if any of you is interested in it, is actually unstable and it's very, very hard to control. And it's just, even like there are experiments and even very skilled riders are not able to balance on this kind of bicycle. These are all considerations you can find on the paper, but then in here we want to see, okay, what does it look like? What happens from a mathematical point of view? Well, we start with a neutral bicycle. We have transfer function is basically the same as before. It's just that now v is negative. This model is unstable and unstabilizable. So the neutral model is just impossible. You cannot do anything. How can I see this? Well, there is one criterion which I haven't mentioned before. When you have a transfer function, we said that we want all roots to be negative, all the poles of the transfer function to be negative. There is one condition that you can check in order to have all eigenvalues with the same sign, which might be also all positive, but at least you know that they have the same sign. This necessary condition for having the same sign is that the coefficients in front of each term, so here we have 1, the coefficient is just 1. Here we have all this coefficient in front of s, and here we have all of this, because it's just the term we know s. These three terms need to have the same sign in order to have the same sign also for all the eigenvalues. Well, in this case, it doesn't happen because this one, the coefficient is 1, it's positive. In this one, all of these quantities are positive, but v, because v now is negative. The bike is going backwards. So since we have a change of sign in here, it means that the eigenvalues will not have the same sign with the controller, because the controller is already in. If the eigenvalue will not all have the same sign, it means that there is at least one positive eigenvalue with the controller. So even when we control it, we have instability. This is the concept behind it. I know it's very abstract. This is called Routh criterion. It is not strictly necessary for this course, but it's something I wanted to mention to give you an understanding of, you look at a transfer function and say, oh, this is actually, like the eigenvalues might be actually all negative or not. Because if they're not all of the same sign, you know that there's at least one which is in the right-hand plane. So we introduced the front fork because the neutral model is anyway useless. And I will not do the math here because you remember how big the front fork, the transfer function of the front fork was. But the problem is not solved. The problem is not solved with a normal controller. A mathematical solution can be found with a control action, which is something we do not cover in this course because it's an advanced control topic, which is called H-infinity optimization. So with the H-infinity optimization, we end up with something which phi goes to 0, phi dot goes to 0, and delta goes to 0. It doesn't solve the problem. Mathematically, it's fine. Practically, if you're a rider, this here is an instantaneous change of delta. So it's not about having a neuromuscular delay which is very, very small or whatever. It has to be instantaneous, otherwise the bike is not stabilized. This is why it's so hard to drive it, because even a very advanced control system leads to solutions which are not really feasible in reality. So this was just to give you an example of bicycle controller in order to somehow sum up everything that we mentioned last time. So now you have a good knowledge of systems theory, a good knowledge of control theory, and a good example, which is all this bicycle, where you have both the modeling part and the control part. So a bit of analysis and a bit of synthesis. So again, As I also said last time, I used some material for preparing these slides, for preparing this lecture, but these are concepts that have been around for a very long time. So feel free to investigate on any book, any slides that you find around, because there's a lot of high quality material about all of this. And again, this is the paper on the bicycle. I will share it with you. It's publicly available on the internet. And I will also give you this extra report that I prepared with colleagues, where there are some more details than this paper, so you can actually understand the physics behind it and everything is behind this if you want. So this was all about control theory. I will see you in the next lecture, and thank you for your attention.